I'm a bad guy, and I just want to kill someone right now. Do you have any final words? Actually, yeah, I want to take this time to discuss the revolutionary technology called the MRI. Oh, okay. MRIs, or more formally known as magnetic resonance imaging, is a non-invasive way of getting detailed images of almost every internal structure in your body without the use of radiations. But before we learn how it does this, we need to understand the history of an MRI. This all started with the study of electrons and atomic nuclei's response to magnetism in the 1930s by this guy, physicist Isidor Isaac Rabi. He was developing a way to measure the magnetic properties of an atom, or, in scientific terms, this is called the spin. What he did to do this is by inventing the NMR, a nuclear magnetic resonance, to research the sodium and potassium content in a living cell. He realized with this technology that he could make a magnetic resonance body scanner, later proposing this idea, creating the groundwork for the now known MRI, which looks like this. 10 years later, in 1940, physicists Felix Bloch and Edward Purcell studied the atomic and molecular magnetic resonance properties of solids and liquids, leading them to win the Nobel Prize. This research helped the development of the MRI technology greatly. A pivotal moment for the MRI came in 1969 with the physicist Dr. Raymond Damien, who hypothesized magnetic resonance could differentiate cancer cells from non-cancerous cells in the body, which he successfully demonstrated with a rat. While finding this life-changing information out, he discovered that different tissues emit different response lengths, leading him to create and propose the idea to use the NMR for medical imaging, aka an MRI. In 1972, Damien files his first patent for his new MRI technology. 2 years later, he designed and built the first MRI machine called the Indomitable. It looked like this. Later, on the fateful day of July 3, 1977, Damien achieved the first NMR imaging of Larry Minskoff's chest, showing his heart, lungs, vertebrae, and musculature. This was later dubbed the first MRI image. Capitalizing off this idea, Damien founded the Forner Corporation, aka the Field Focused Nuclear Magnetic Resonance Corporation, producing the first commercially available MRI while innovating it from creating the first portable MRI to ones compatible with pacemakers. While Damien's work is Nobel Prize worthy to many, the Nobel Prize Committee would disagree with you. Instead, they would give this Nobel Prize to Sir Peter Mansfield and Lautenberg in 2003, people who merely just slightly innovated on Damien's version of the MRI.
But you can't do this to me. I started this company. You know how much I sacrificed?
While now MRIs are commercially available, they aren't cheap. They cost anywhere from $225,000 to $500,000. You got all that, right? Well, it doesn't really matter, because now we get to move on to the best part, the physics of the MRI. Before we start talking about the physics of an MRI, we need to make one thing clear. The MRI we will be specifically talking about is called the closed-bore MRI machine. This is because this is the most common one and it's the easiest one to explain the physics for. The closed-bore MRI machine is basically just a big solenoid, with it having a coil running a current and a magnetic field. An MRI uses its magnetic field and radio waves to map and create an in-depth image. They do this by specifically using the hydrogen molecules found in our body. This is because the hydrogen molecule, which can also be referred to as a proton, is being positively charged, so it can act like a magnet. This means that the proton has both a north and south pole, creating its own magnetic field, just like a bar magnet. This magnetic field creates the hydrogen molecule to spin on its own axis, kind of like a top. This is called its precision. The problem is each hydrogen molecule spins in every random direction, which makes it impossible for the MRI machine to actually create an image. This is where the MRI's strong magnetic field comes into play. Its magnetic field, commonly called the B0 field, forces the hydrogen molecules to align itself with the B0 field. due to how much stronger it is compared to the magnetic field of the hydrogen molecule. These hydrogen molecules do not physically move to align itself with the B0 field. Instead, they act like a compass needle, spinning so it faces towards the north side of a magnetic field, kind of like this. So this is how the hydrogen molecule moves, so it faces towards the B0 field. Instead of physically moving, it rotates to match the B0 field, kind of like this compass, because this compass rotates to match the magnetic field. As we can see here, it's only rotating but not physically moving to match the B field. Some of these hydrogen molecules will line up with, parallel, or against, anti-parallel to the B0 field. And due to quantum physics, we know that more hydrogen molecules will line up parallel to the B field, while the rest of the hydrogen molecules will cancel out due to their magnetic fields going in opposite directions. These extra hydrogen molecules' magnetic field is called the net magnetization vector. This net magnetization vector's spin is affected by the B0 field. The stronger this field is, the faster the spin will be, giving us a precisional frequency, which can be calculated by using Lammer's expression. We won't be going into Lammer's expression due to how complicated it is, but this is what it is. The precisional frequency and the axis alignment of the hydrogen molecules is the first set of information the MRI uses to create an MRI image. The next step into getting an MRI image is using radio frequency pulses. These radio frequency pulses are used to flip extra protons, aka our net magnetization vector, out of alignment from the original B0 field. These radio frequency pulses flip it so that the net magnetization vectors are 90 degrees, making it perpendicular to the original orientation. This means it gains transversional magnetizations while getting rid of its longitudinal magnetization. This flip doesn't last forever though, so as it returns to its original orientation, it gains its longitudinal magnetization while losing its transverse magnetization. This may seem confusing, so here is a physical representation of what's happening. If we were to assume this was the hydrogen molecule's original position, we could see it has only longitudinal magnetization and no transverse magnetization. But as the hydrogen molecule rotates, it loses longitudinal magnetization and it gets turned into transverse magnetization until there is no more longitudinal magnetization and only transverse magnetization. The same can be said when it's rotating back to its original position. As it rotates back to its original position, it loses its transverse magnetization and gains its longitudinal magnetization, as we can see right here. And once it's fully rotated back to its original position, it's back to only having longitudinal magnetization and no transverse magnetization. This loss and gain of both the longitudinal and transverse magnetization produces a magnetic field spiral, producing an electrical signal called an echo. This whole process is called the free induction decay. If this sounds familiar, this is because the free induction decay is basically just the real-life application of our first right-hand rule. This is because our magnetic field spiral would be our fingers, while our echo, aka the electrical signal, would be our thumb, which is basically just the first right-hand rule. Finally, to obtain an image, when these hydrogen molecules realign with the B0 field or their original position, as stated before, it gains longitudinal magnetization while losing its transverse magnetization. This gain of longitudinal magnetization is called T1 time, while this loss of transverse magnetization is called T2 time. Through many scientific experiments, we figured out that every tissue releases a different amount of T1 and T2 time. Knowing this, the coil in the MRI can detect this T1 and T2 time and use the mathematical equation called the Fourier transformation, which looks like this, to convert this information into an image. It also uses the other information that we learned prior, such as the echo or the free induction decay, to create a more precise and accurate image. So now I finally taught you about how the MRI works. I can finally die in peace. Oh my god, that was so educational. If I was a teacher, I would give this project 101%. Anyways, I don't want to kill you no more, so you're free.
Bota na boca, bota na cara, bota onde quiser. Bota na boca, bota na cara, bota onde quiser. O novinho me olhou e quis comer minha pepequinha. Hoje eu vou dar pro novinho, fode a Laricinha. O novinho me olhou e quis comer minha pepequinha. Hoje eu vou dar pro novinho, fode a Laricinha.